This is just an example using conservation of mass and momentum and a little bit of hydrostatics. So this is the problem of a flow. You can think of it as a river going through an open channel and through gates, and those gates are slightly open at an angle theta. The length of each gate or the width of each gate is W, and obviously the width of the channel is 2W. The parameters are given here, and we're going to carry them through. And the key point here is that we assume that the water level jumps suddenly at the exit of the gates. So, as far as our assumptions are concerned, and the choice of the control volume, for our assumption we're going to use steady flow, frictionless as well. And we are going to assume that rho, the density of water, is equal to 1000 kilogram per meter cube. The CB, the control volume, is outlined here, and I am going to name those surfaces by their normal. This is normal. This is surface 1, 2, 3. So remember, the normal is always pointing outward, okay? And that's surface 4. And I can already list all the forces. So in terms of forces, I will have the force exerted by inertia, so V1, and outline here, the force exerted by inertia at the exit, V2, then the force of pressure. So what is that force of pressure? FP1, FP2, and FP3, those are hydrostatic pressure forces on those sections. And R is action of gate on flow. So what we are after is really minus R, okay? So how are we going to solve this? The only equation that we know that contains forces is the conservation of momentum. For conservation of momentum, we need to know the momentum at each section. But we don't know the momentum at section 2. We don't know V2. So in order to know V2, we need to apply conservation of mass. And this is the equation of conservation of mass, right here. Now, conservation of mass is going to be between those two surfaces, V1 and V2. There is no mass exiting or entering through 3 or 4, for obvious reason. The flow is steady, so this is 0. And I'm going to have the integral over S1 plus the integral over S2 is equal to 0, which translates into minus rho V1 H1 W plus rho V2 H2 W 1 minus sine theta, and that's equal to 0. Alright, so what is all of this? This is the surface area of section 1, H1 times W, and this is the surface area of section 2, 1 minus sine theta W, and the reason obviously is that I have the angle theta here by trigonometry. This the width here is W1 minus sine theta. So V2 is equal to H1 over H2 1 minus sine theta V1. When you plug all the number, h1 is 3 meters, h2 is 2.75 meters, sine theta it's sine 50 degrees, and v1 is 0.8 meter per second, you get v2 is equal to 3.73 meter per second. So that's your momentum in section 2. So now that we know the momentum in section 2, let's write our conservation of momentum equation that is shown here. So again, we have flux of momentum only through S1 and S2, nowhere else. And so due to the normals, I can directly write that the flux of momentum through section 1 is minus rho v1 square. So why is there a minus? Because the velocity and the normal are in opposite directions. So minus rho v1 square times the surface area, which is h1w, plus, now in section 2, velocity and normal are in the same direction, so we have plus rho v2 square h2 w, and again that 1 minus sine theta, and all of this is equal to so all of this is in the direction I, assuming that we use this frame of reference I j, and then all of this is equal to fp1 plus fp2 plus fp3 minus r. So let's expand all of those. fp1, fp2 and fp3 are the hydrostatic pressure forces onto the section, and the forces on the vertical wall are so for fp1 that's going to be rho gh1 square over 2 times w, and it's the I direction. Again, check the definition to figure out the signs of that force. fp2, actually fp2 is going to be minus rho g h2 over h2 square over 2 w 1 minus sine theta, also in the I direction, plus rho g, well, I'm going to run out of space here, so it's very best that I'm writing that down. Actually, it's going to be minus rho g, so that I'm writing hp3 right now, h1, because we assume that through the gates the depth of the water is h1, w cosine theta, that's the width of the section, j plus r. So here we go. Now we have everything we need, and we can write along x or along I hat I have Rx is equal to all the terms in I, and so if I break it down, I'm just going to write the numerical value and not rewrite all those equations, but the contribution of the momentum V2 is 17.9 kilonewton. The contribution of V1 is 3.8 kilonewton. The contribution of FP2 FP2 is minus 16 kilonewton, and the contribution of FP1 is plus 82 kilonewton. The net force is minus 52.3 kilonewton, and so that the force is going this way. Along J, Rx is equal to minus FP3, and that's 56 kilonewton. So in short, the force F, the action of the fluid on the gate, is 52.3 I minus 56 J in kilonewton. So the force is going down as we could expect.